Welcome back, guys. We're going to do the graphs of polar functions today. And after doing the exploration, hopefully you've already done that on Desmos, you'll have a better idea of what polar functions look like, how to get the different shapes, how changing the values can affect the shapes. So now that we can get into the actual notes for the graphs. So you should be putting these in your notebook. As you go through, we've been given the unlimited version of Screencastify now, so you should be able to view this all in one video now. We don't have to just do 5-minute segmented videos anymore. So if you need to pause it and write your notes down, feel free to do that as well. Also remember, if you're having any questions on the notes or the assignments as you're doing it, please email me, just as if you would come into class and ask questions, before or after school or during class. All right, think of it like that. You can just shoot me an email anytime if you're just working on an assignment and have a question. So when we're graphing polars, so if we were graphing this function, so we've got r equals 2 cosine theta. We could easily graph it on the graphing calculator using polar mode or on Desmos, but just to see how to graph it using point plotting. So theta is our independent variable, r is our dependent variable. So you can pick any values you want for theta that fit in the domain, which in this case, the domain would be all reals, all right, because you can take the cosine of any number. But we'd want to pick values of theta that we can evaluate. So multiples of pi over 6, pi over 4, pi over 3, anything like that. So these are the values that I've chosen for theta, and then we evaluate the r values. But just remember, if you are actually writing the coordinates, we write r comma theta when we're doing polar equations. So the r value would come before the theta, even though theta is the independent variable. So if we wanted to plot these points, so r is 2, theta is 0. So we're going to be on the theta equals 0 line, but we're going to be 2 units from the pole. So that would be this point right here. Then pi over 6 root 3, we're going to be on the pi over 6 30-degree line. And we're going to be square root of 3 radians from the pole. Then theta is pi over 3. We're going to be on the pi over 3 line. R is 1, so we're going to be positive 1 units from the pole. And then at pi over 2, we get r is 0, which means you're going to be at the pole. Any point where r is 0, it doesn't matter what theta is, will end up being here at the pole. Now the next point, r is negative 1, theta is 2 pi over 3. So 2 pi over 3 is actually over here. But since r is negative 1, you have to go in the opposite direction 1 unit. So that's why we get this point over here. And then at 5 pi over 6, that would be this line here. But since r is negative root 3, we're going to go square root of 3 units in the opposite direction, which brings us here. And then negative 2 comma pi. R is negative 2, theta is pi. So pi would be right here, but since we have negative 2, we go backwards 2, and we end up at this point. And then what happens, I didn't include as many points, but what happens is that these points all end up repeating again and again. So you can actually get this entire graph by just setting the domain from 0 to pi. If you're doing this on the calculator and you set your theta min and theta max 0 to 2 pi, it still gives you the same graph, but what happens is it draws the circle and then it traces over it again. Right? And if you set theta higher, it just keeps going over and over and over again. Right? If you have negative theta values, it just includes the ones going in the opposite direction. So this would be our full graph. So some of the things we like to find for polar graphs are zeros and maximum values. The reason why it's good to know the maximum values is because if you're doing it on the calculator, you want to know what to set your window up to. Okay, so in this case, the biggest value for x we're getting is 2. So if you're setting up a window for x and y, you need to make sure that you only have to go up to, I'd usually go bigger than 2. So 3, 3, negative 3, negative 3 to make sure that you have all those values. All right. So when we were doing the exploration, you probably saw that anything in this format, a cosine theta gave you a circle with a diameter of a. So circle, this should actually say radius 1, not radius 2. The diameter is equal to 2. Right, the radius is actually equal to 1, right, because the center is here. All right, so this value right here represents the diameter, not the radius. And if it was negative, then you end up getting a circle over here. If you use sine instead of cosine, you end up getting a circle that was centered on the y-axis. And then if you had the negative value, it ended up down here. All right, but anything in the form of a cosine theta or a sine theta gave you this circle, all right, that was either on the x or the y-axis. So sometimes finding the zeros or the maximum values are something that we want to find as well. All right, so for the graph here, so the maximum value is the furthest point from the pole. So in this case, the maximum value, we always do absolute value. Since r is a distance from the pole, it doesn't really matter if r is positive or negative. So that's why we do absolute value. But the biggest value that can be is 2. And it occurs at 0 and 2 pi. And it also occurs at other values besides these as well. Now the zeros we can get by setting r equal to 0. For rectangular functions, when we talk about zeros, we usually talk about the x-intercepts. But for polars, when they ask for the zeros of a polar, it's when r is 0. All right, so in this case, r is 0 at pi over 2 and 3 pi over 2. But remember, it's also going to happen at negative pi over 2, 5 pi over 2, any odd multiples of pi over 2. Okay, so let's look at another example. Okay, so this is a question that we could be asked to evaluate. So to find the maximum value of the absolute value of r for this function, and the zeros, and we could also verify by graphing it on the calculator or using Desmos if you don't have your own graphing calculator at home to do that. So if we're trying to find the zeros first, that means we're replacing r with 0. All right. So we set the function equals 0, and now we're just going to solve this algebraically the same way we did in section 4.5. So we're going to subtract 1, divide by negative 2. So that will give us positive 1/2 equals cosine theta. And then we just have to use the unit circle and figure out, well, when does cosine of theta equal positive 1/2? So you'll see that the first value happens at pi over 3. And then the next one happens at 5 pi over 3, or you could also say negative pi over 3. So it's a little shorter to write it like this. So at pi over 3 and negative pi over 3 plus 2 pi n, because remember, the coterminal angles, right? If you keep adding or subtracting 2 pi to pi over 3 or negative pi over 3, you get values where cosine will equal 1/2 as well. So because these graphs constantly repeat, there's usually going to be an infinite number of zeros, right? If there's 1, there's probably going to be an infinite. To find the maximum value, we want to think about what the maximum and minimum values are of cosine of theta. Okay, so remember when we graphed cosine graphs, we saw that the amplitude was 1. So the biggest cosine of theta can be is 1, and the smallest value of cosine of theta is negative 1. So if we replace cosine of theta with 1 and negative 1, that should give us the biggest values possible for r. So replacing cosine of theta with negative 1, we get 1 minus 2 times negative 1, so that would be plus 2, which gives us 3. And if we replace cosine of theta with positive 1, we get 1 minus 2, which is negative 1. So if we take the absolute value of both of these, the biggest value would be the 3. And then if we wanted to do a quick sketch on the calculator just to check, when we graph it, you should get this graph. Okay. And if you hit trace, it actually starts the graph here, and then it starts to revolve. So this first time it equals 0 is at pi over 3. And then when you revolve again around here at 5 pi over 3, all right, it'll be 0 again, and then it will keep repeating over and over again. That's why there's an infinite number of zeros. All right. And then the furthest point from the pole is over here, and we can easily count 1, 2, 3. It is 3 units from the pole. All right, so that's why that's our biggest value. Okay, so the last thing we're going to do is some sketching, and we're going to be able to use Desmos or the calculator to sketch, but sometimes we want to identify some exact points as well. So some of the questions on your homework are going to ask you to do this. So it says to sketch and label 3 points in polar coordinates for this function, r equals 5 minus 3 sine theta. So the first thing we're going to do is sketching it, and you can use Desmos or you can use the graphing calculator. So I'm just going to show you on the calculator how we would set it up. So the first thing you'd want to do is make sure that you're in radian mode, and then make sure you're in polar mode. So when you press the mode button, all right, make sure you've got radian and polar highlighted. Then we're going to go to our y equals, which when you hit y equals, now it all of a sudden becomes r equals, because now we're in polar mode. So we're going to type in the function, r equals 5 minus 3 sine theta. And when you hit the variable button now, theta shows up because we're in polar mode. Make sure your plots are off, or else that's going to possibly not make your graph appear. So make sure all the plots are not highlighted. So now before we graph it, we want to set up a window. So this is where knowing the maximum value is going to be helpful. So think about this. So sine of theta, the biggest sine of theta can be is 1. So that would give you 5 minus 3, which is 2. And then the smallest sine of theta can be is negative 1, which would be 5 minus 3 times -1 is -3. So 5 plus 3 would be 8. So the biggest value we have for r is 8. So I want to make sure that when I'm setting up my window, x min and x max, y min and y max include 8. So I just went from -10 to 10, -10 to 10 to make sure that I included them. And then a good theta min and max, 0 to 2 pi. And your theta step is pi over 24. And it just converts it to a decimal for you. So if you set up the theta min as 0, theta max as 2 pi, theta step as pi over 24. And then again, the reason why I picked these values for x min, x max is because I found the biggest possible value for r was 8. All right, so I just wanted to make sure I went a little bit past 8 so we can see the full graph, which gives you this, which is a cardioid graph. All right, so it gives you, it's almost like a heart shape. Sometimes this is called a dimpled limosome curve as well, because it doesn't quite go through the origin. It's not quite a perfect heart shape. So now that we have this graph, so now it says to label 3 points in polar coordinates. So we're not going to use trace and find decimal values. We want to find the exact values. So since we were able to use technology to sketch the graph, we're going to want to find the 3 polar coordinates algebraically using the function. All right. Don't try to identify the points by looking at the graph, because remember, a polar point has many different possible coordinates. All right. So there's more than one way to represent a single point. So you don't know which one is technically on this equation. So we want to make sure we're using the equation first and then identifying the point. Okay, so the first thing we did was sketch it. Now we're going to identify the points. So here's our same curve that we just sketched, all right, which is kind of our dimpled limosome curve. All right, not quite a cardioid, but we're allowed to pick values we want for theta, since theta is the independent variable. So I'm going to pick the easiest values possible. So starting with theta is 0. You can choose any ones you want, but I like to pick zeros and pi over 2s or anything that's going to maybe avoid square roots. So now we can just take that value for theta and plug it into the function given. So 5 minus 3 sine 0, and we should know that sine of 0 is 0. And that will give us r is 5. So our coordinates are comma theta. All right, remember these are polar coordinates, not rectangular coordinates. So r is 5, theta is 0, which would be the point located here. Theta is 0, and then we have 5 units from the pole. Again, find the coordinates, then identify it. Don't try to identify it from the graph, because again, there are many representations for this, for polar points. Okay, so for another value of theta, we could pick pi over 2. You could also pick pi over 6, because that would give you 1/2 for sine. But again, we'd still get a fraction here, so I just made it a little bit easier by picking pi over 2. And we want to make sure we're identifying 3 distinct points, which means different points. So if you find coordinates and you end up getting another point that falls here, you want to find different coordinates. We want to find 3 different points on this graph. So when we let theta equal pi over 2 in our function, we have to evaluate sine of pi over 2, which is 1. So that would be 5 minus 3, which gives us 2. So our coordinates in polar would be 2 comma pi over 2. Now identifying this point on the graph, we'd go to pi over 2 and 2 units from the pole. So pi over 2, 2 units from the pole. And this scale is going by 2s. I know it's not labeled, all right, but the scale here is 2, 4, 6, 8. So that's why this point is 5 and this point is 2. So that would be the point right here. And now one more point that we want to find. So another value for theta that we could choose is pi. And we're going to plug it into our function to solve for r. So now we need to evaluate the sine of pi, which is 0. Right? Sine of pi is 0. So we get 5 minus 0, which is 5 again. So the coordinates 5 comma pi. So we want to go to where theta equals pi, which is along this line. And we're going to move positive 5 units. So that means in that direction. So remember, we're going by 2. So 2, 4, halfway in between would be 5. And that's our point right there. Okay, so on the back side or the second page of your homework assignment, it's going to have you do this, sketch graphs and identify 3 points. So you can use technology to sketch the graphs, but I want you to do this to find the 3 coordinates. Okay, use algebra. And remember, you can pick any values you want for theta. So you're not going to necessarily be picking the same points as somebody else, as long as you identify 3 points, 3 distinct points on the graph. Okay, so one of the things is also naming some of these curves, which you maybe saw in the exploration as well. All right, so these graphs right here, the ones with these inner loops, which we saw in one of our examples earlier, these are called limestone curves. All right, and they're found here. And we saw what happens when you switch these values or when one is bigger than the other, if we change one of these to a minus, all right, in the exploration. But these curves with that inner loop, all right, are known as limestone curves. Then we have our rose curves. All right, so you saw these in the exploration as well, where the length of each petal, so this number out in front is A. All right, so if you've got A cosine n theta or A sine of n theta, right, A is the length of each curve. So that's basically your max value of R. And then the n value, down here, it says that you'll have n petals if n is odd, and you'll have 2 n petals if n is even. So right here, n is 3. So that's a rose curve that has 3 petals. If it was sine instead of cosine, it just changes where those 3 petals are. And then for 3 sine of 4 theta, the length of each petal is 3, and the n value is 4. So since that's even, we end up with a rose curve that has 8 petals. So 1, 2, 3, 4, 5, 6, 7, 8. Right. We saw what a cardioid graph looks like. A cardioid graph is kind of that limestone that just doesn't have that inner loop that kind of looks like a heart. And then we also have these, which are figure 8 graphs, which are also called lemniscates. All right, so when you get this type of figure 8 graph, all right, that's called a lemniscate. Okay, so your homework is going to be a worksheet. I'm going to post it on Classroom. All right, and that's going to be due on Tuesday. Okay, and I'll probably set up a Google Hangout for maybe Tuesday afternoon so that we can go over any questions on polars.